Good afternoon. Are you able to hear my voice? Are you able to hear my voice? Is it audible? Yes. Okay. Yesterday we have started the vector calculus. In the vector calculus, there are two subtopics. One is vector differentiation and other one is vector integration. In the vector differentiation, already we have written the results of vector algebra. Whatever we require the results of vector algebra for calculus part, we have written all those. And after that, we have written the position vector of a point and then its continuation. Let us start today's class. So continuation of the last class, third one, vector differential operator. Vector differential operator. It is also known as del operator only. It is also called del operator only. To define three quantities, we require this vector differential operator only. Now it is denoted by the symbol nabla, like this. Name of the symbol is alpha, name of the symbol is beta, gamma, delta, delta. But here it is small delta, this is capital delta. And if you write the reverse of this delta, then we get this. This symbol is called nabla. This is the nabla. We use this symbol for this vector differential operator only. So vector differential operator is denoted by nabla and it is defined as I bar into dou by dou x plus j bar into dou by dou y plus k bar into dou by dou z. It is useful to define the three quantities. One is gradient, next divergence, and then curl. It is just operator only. It doesn't have any meaning. It is not a vector, but in the form of vector only. Like this, d by dx. It is a d by dx is the differential coefficient or operation of differentiation only. And this is the operation of integral operator, differential operator. Like that here, it is also differential operator, but in the form of vector. So that is why it is called vector differential operator. It doesn't have any meaning. It is also not having any meaning. It doesn't have any meaning. If we operate d by dx on some function, then we get some meaningful only. If we operate this on some function, then we get some meaningful only. Otherwise, it doesn't have any meaning. It doesn't have any meaning only. Just like these two operators, it is one operator only, vector differential operator. Because it is also differential operator, but not, it is in vector form. That is why it is vector differential operator only. And it is also called del operator only. That's why we can read this as del only. Actually, name of this symbol is nabla. Because of this symbol for del operator, we are calling this as, or we are pronouncing this as so del or del operator. You can read this as del only. But actual name of the symbol is nabla, like this. Next, its continuation. Fourth one. Gradient of a scalar function. Gradient of a scalar function. If phi of x, y, z equal to 0, already we know that y equal to f of x represents a curve in two-dimensional space. Z equal to f of x comma y represents a surface in 3D space. And u equal to f of x, y, z represents hypersurface in 4D space. It is 2D space, 3D space, 4D space only. So this is the equation of the surface. But out of 3 variables, 1 variable is written in terms of other 2 variables. This is in explicit form. The same function with the 3 variables written in other form, that is phi of x, y, z. Phi of x, y, z equal to 0. This is in implicit form only. Both are same. Both are the relations in terms of 3 variables. It is in explicit form. This is in implicit form. It is a equation of surface. That is, it is also equation of the surface only. Throughout our vector calculus, we consider this as equation of surface only. So if phi of x, y, z equals 0 is a equation of surface, then the gradient of a scalar function phi of x, y, z is denoted by nabla phi, or we call this as del phi, or grad phi, and defined as del phi or nabla phi equal to grad phi equal to dou phi by dou x into I bar plus dou phi by dou z into j bar plus dou phi by dou z. So this is dou phi by dou y, here dou phi by dou z into k bar. That is, we are operating this operator on scalar function phi. And this converts the scalar function to vector function, because on right hand side we have the in terms of ijk only. Right hand side is in terms of ijk. Input is phi. This phi is scalar function, but output is in terms of ijk. It is a vector function. So the gradient converts scalar function to vector function. Gradient converts scalar function to vector function only. Now, next we'll discuss about this gradient. Note point 1. Here the equation of the surface is phi of x, y, z equal to 0. It is the equation of the surface. I'm taking the d on both sides. That is differential on both sides. d phi equal to d0. Differential means change in one quantity only. Change in constant is 0 only. Change in phi. In the total and partial derivatives, the partial and total derivative topic, already we have written the total derivative and total differential. Already know how to write the total differential of this function of 2 variables only. Because u is given in terms of 2 variables x and y. After this, x and y are not given in terms of any other variable. So we start at u, we go to x, and we stop there. And again, we start at u, we can go to y, we stop there. So du equal to dou u by dou x into dx plus dou u by dou y into dy. Like this, we write the d phi for function of 3 variables x, y, z only. Here phi is given in terms of 3 variables x, y, z only. So dou phi by dou x into dx plus dou phi by dou y into dy plus dou phi by dou z into dz equal to right hand side change in constant is 0 only. Next, here this gradient phi is vector, del phi or grad phi is a vector. It is given by dou phi by dou x into I bar plus dou phi by dou y into j bar plus dou phi by dou z into k bar. Now we are going back to this. Here this dr bar is also vector. dr bar equal to dx I bar plus dy j bar plus dz k bar. If you write the dot product between del phi and dr bar, if you write the dot product between del phi and dr bar, then we get the dou phi by dou x into dx plus dou phi by dou y into dy plus dou phi by dou z into dz. So that is same as this. So this sum is same as the dot product of two vectors. One is del phi dot dr bar equal to 0. Between two vectors dot product is 0. Between two vectors dot product is 0, then we can say that the two vectors are perpendicular only, because a bar dot b bar equal to modulus of a bar into modulus of b bar into cos. So when theta is 90 degrees, cos 90 is 0, then dot product is 0 only. Between these two vectors del phi and dr bar, dot product is 0. Therefore, we can say that del phi is perpendicular to dr bar only. Here del phi is perpendicular to dr bar. X, Y, Z. Some object in space. Some object is in space. On the surface of this object, we consider one point P. P is any point X, Y, Z. If P is a point X, Y, Z in space, then its position vector means OP bar. That is same as R bar. So R bar equal to Xi bar plus Yj bar Zj bar only. So Xi bar Yj bar plus Zk bar only. So P is any point in space, then its position vector is R bar. At this point on the surface, if we draw a tangent plane, at this point to the surface, if we draw a tangent plane like this, then this dr bar, the dr bar lies along the tangent plane only. This dr bar lies along the tangent plane only. If any line touches the curve, this line is called tangent to the curve only. And this point is called point of contact. At this point of contact, if we draw a line perpendicular to this tangent, then this is called normal only. If this is tangent, this is normal only. And for this shape of the curve, we take this as positive direction of normal, this as inward direction, that negative direction of normal only. So the shape of the curve is like this. It is a tangent, this is the normal, and this is this. For this shape, we take this as positive direction only, this as inward direction. Now, if we draw a one vector, perpendicular to this dr bar, then this is the normal to the surface only, right? It is some object in space. On the surface of this object, we take one point. At this point, dr bar is the position vector of this point. So this r bar is the position vector of this point, and dr bar lies along this tangent plane to the surface only. For this vector dr bar, if we draw one vector perpendicular to this, then such a vector is normal vector to the surface only. But here, for this equation, its equation of the surface is phi of x, y, z equal to 0 only. Phi of x, y, z equal to 0 only. For this equation of the surface, already we have shown that here del phi is perpendicular to dr bar. Del phi is perpendicular to dr bar. Here dr bar is along the tangent plane to the surface at point P only, right? And del phi is perpendicular to dr bar means this del phi lies along the normal to the surface only. That is why we use this gradient quantity. To find the normal to any given surface. We use this gradient quantity to find the normal to any given surface because of this one. Right? It is about gradient. Finally, this gradient gives normal to any given surface only. we are operating this del operator on scalar function, and this converts the scalar function to vector function. Next, fifth one. Directional derivative. In short form, DD. For function of one independent variable, the derivative is written as dy by dx only. For function of three variables, u equal to f of x, y, z, the derivatives are written as dou u by dou x, dou u by dou y, dou u by dou z only. So here dy by dx means it is a change in one quantity y corresponding to change in other quantity x only. Or geometrically it is the slope of the tangent to the curve only. Physically this gives a change in one quantity corresponding to change in other quantity only. Like that here, dou u by dou x is also change in one quantity u corresponding to change in x only. Dou u by dou y gives change in u corresponding to change in y. Dou u by dou z is change in u corresponding to change in z only. Z, y, x only. It is a ordinary derivative. Dy by dx is ordinary derivative, and these derivatives are partial derivatives. To find the partial derivative dou u by dou x, we find the derivative of u with respect to x by treating other two variables as constant. That is, we are finding the change in u in the direction of x-axis only. So ux gives the rate of change of u along the x direction. Similarly, uy gives change in u along the y direction only. While finding the change in u along the y direction, we keep other two directions as constant. That is why we are treating xz as constant. We are finding the derivative of u along the y direction. Similarly, uz gives the rate of change of u along the z direction. While finding the change in u along the z direction, we keep other two directions as constant. So ux is change in u along the x direction, uy is change in u along the y direction, uz is change in u along the z direction. These three derivatives are change in u along the coordinate axis directions only. These three are the change in u along the coordinate axis direction. But always we may not require the change in u along the coordinate axis. Sometimes it is required to find the change in u along some other direction. If you want to find the change in some direction like this, in such direction, if you want to find the change, such a change is the directional derivative only. Only along the x direction, change in u is ux only. Along the y direction, change in u is uy. Along the z direction, change in u is uz. If you want to find a change in some other direction, such a derivative in that direction is the directional derivative, or in simple way, derivative of u in any given direction is called directional derivative only. Other than coordinate axis, if you want to find the derivative, such a derivative is called directional derivative or derivative in some given direction. So directional derivative means derivative in any given direction is called directional derivative other than coordinate axis only. This is one way. Or other way, we define like this. Z-axis, y-axis, x-axis, some object in space, and we are taking one point on the surface of the object. Already, we know that del phi, that is gradient, gives a normal to the surface only in outward direction. If you find the del phi at this point, this del phi gives a normal to the surface at a point P only. So at this particular position on the surface, this del phi is fixed only. Normal is in this direction, it is fixed only. If any some other vector a bar makes an angle theta, if any vector a bar makes an angle theta with del phi, then the projection of this del phi, in the direction of a bar, the projection of del phi in the direction of a bar is also called directional derivative, or the component of this vector del phi in the direction of a bar is also called directional derivative only. And it is given by, directional derivative is given by the projection of del phi in the direction of a bar is given by del phi at p dot a bar by modulus of a bar only. This is the projection of vector del phi in the direction of a bar only. So to find the directional derivative of any given function at a particular point in some given direction a bar, we try to use this formula only. So simple way, directional derivative means derivative in any given direction only. Derivative of the function in any given direction, in any arbitrary direction, not along x-axis, y-axis, z-axis. Other than coordinate axis direction, if you want to find the derivative, then such a derivative is called directional derivative. That is arbitrary direction in space. Or we can define it like this also. The projection of this vector del phi in the direction of a bar is also called directional derivative only. Between these two we have angle, so we can express this also in terms of angle. This is equal to modulus of del phi at p into modulus of a bar by modulus of, that is inside the modulus a bar by modulus of a bar into cos theta. First of all, a bar by modulus of a bar is unit vector. The length of unit vector is 1. So this is 1. This is equal to just modulus of del phi into cos theta. With this cos theta, we can write the maximum value of this directional derivative and minimum value of this directional derivative only. Since minus 1 less than or equal to cos theta less than or equal to plus 1. We know that cos theta lies between minus 1 plus 1. 1 is the maximum value for cos, minus 1 is the minimum value for cos only. And this maximum value 1 occurs when theta equal to 0. This maximum value 1 for cos function occurs when theta equal to 0 only. With this maximum minimum values of cos, we can write the maximum minimum values of this directional derivative only. Here we require the modulus of del phi, which implies minus modulus of del phi less than or equal to modulus of del phi into cos theta less than or equal to 1. That is modulus of del phi. Right? Therefore, this modulus of del phi cos theta is same as directional derivative only. Minus modulus of del phi less than or equal to dd less than or equal to modulus of del phi. This is the maximum value for directional derivative. It is the minimum value for directional derivative, or it is the magnitude of greatest rate of change of directional derivative. It is the magnitude of greatest rate of change of directional derivative. It is the magnitude of lowest rate of change of directional derivative. Because of plus, it is outward direction. Because of minus, it is negative direction, inward direction. Right? Maximum, minimum values of this directional derivative only. And this maximum 1 occurs for cos when theta equals 0 only. In the same way, this maximum value modulus of del phi occurs for directional derivative when theta equal to 0 only. Now see this figure. This maximum occurs when theta equals 0 only. When theta equals 0, what happens here in this figure? Theta equals 0, this direction vector a bar coincides with the normal vector del phi. So this maximum occurs when theta equals 0. In this case, this direction vector coincides with the del phi. So from this we can say that the maximum occurs in the direction of normal, because a bar is same as del phi when theta equal to 0. This is about directional derivative. Now first of all, directional derivative is same as derivative only, but finding the derivative of the given function in any arbitrary direction is the directional derivative. Finding the derivative in a particular arbitrary direction is the directional derivative only. To find the directional derivative, it is a formula. Okay, we read the definition. If phi of x, y, z equal to 0 is a equation of surface, then the rate of change of a scalar function phi of x, y, z at the point p, x, y, z, then the rate of change of scalar function phi at the point p of x, y, z in the direction of given vector a bar is called a directional derivative. In short form dd of phi in the direction of a bar. And it is given by dd equal to del phi suffix p dot a bar by modulus of a bar. So it is the formula to write the directional derivative of any given function, that is given scalar function, in the direction of a bar at a point p. Note point. The maximum rate of change or the greatest rate of change or fastest change of a scalar function phi of x, y, z occurs, the maximum rate of change or greatest rate of change or the fastest change of a scalar function phi of x, y, z occurs at a point p of x, y, z in the direction of normal vector to the surface phi equal to 0 when theta equal to 0. Next, note point number 2. The maximum and minimum values of directional derivative, the maximum minimum values of directional derivative of phi of x, y, z at the point p of x, y, z are given by modulus of del phi suffix p and minus modulus of del phi suffix p. From the previous page, this is the maximum value, this is the minimum value. We're writing same thing here on. So this is about directional derivative. Derivative in any given arbitrary direction. Derivative of the function in any given arbitrary direction is called directional derivative. This is about directional derivative. Next, sixth one. Divergence. Divergence of a vector function. If f bar of x, y, z equal to f suffix 1 of x, y, z into I bar plus f2 of x, y, z into j bar plus f3 of x, y, z into k bar, or in short form we write this as f bar equal to f1 I bar plus f2 j bar plus f3 k bar. Both are same. We are the same vector in short form like this. Is a vector function. Is a vector function. Then the divergence of a vector function. Divergence of a vector function f bar is denoted by the symbol del, that is nabla symbol. After nabla symbol dot, after dot operation f bar, or small letter d, small letter I, small letter v, div f bar, and defined as del dot f bar equal to div f bar equal to dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. Here, this operator, del operator, is operated on vector function with dot operation only. If we operate the del operator on scalar function, the resultant is vector function. If you operate the del operator on vector function with the dot operation, this will give the scalar function only. So gradient converts the scalar function to vector function. Divergence converts the vector function to scalar function. So for this input f vector f bar, for output no ijk, so it is scalar function only. Because a scalar function, if we calculate this del dot f bar at a particular point, the output will be scalar constant, some value only. Now, if we calculate del dot f bar at a particular point in space or at any flow, in any flow of quantity, if we calculate this del dot f bar at a particular point, this may be 0, may not be 0, two possibilities only. Again, not equal to 0, this may be greater than 0 or less than 0. So these are the possibilities only. If we calculate this divergence at a particular point in a flow of quantity, here I am saying that flow of quantity, this flow of quantity may be electric flow or magnetic flow or fluid flow or air flow. There are different types of flows. Here the flow means that may be electric flow, magnetic flow, or fluid flow, or electric or air flow, any flow only. Initially, this vector calculus is is applied to study of nature of the fluid flows only. Later on, it is applied to electric flow, magnetic flow, and air flows only. So if we calculate the divergence at a particular position in a flow of quantity, these are the possibilities only: equal to 0, greater than 0, less than 0. Using these results, mathematically we can say that whether the flow expands or contracts at a particular position in a flow of quantity only. By calculating this divergence mathematically, we say that whether the flow is expanding or contracting only, whether the flow is expanding or contracting only at a particular position. Suppose the divergence is greater than 0, we can say that the flow is expanding only. We can say the flow is expanding or flow is like this, away from the point. That is diverging only. The flow is expanding at a particular position only. Suppose the divergence is less than 0, then we can say the flow is contracting only, That is, or the flow is towards the point. The flow is towards the point only. This is just like source, this is just like sink only, right? Suppose the divergence is 0, we can set the rate of inflow will be same as rate of outflow at a particular point P only. Right? So we can say the flow is expanding or contracting or no change in the rate of flow. Whenever divergence is 0, the rate of inflow will be same as rate of outflow. No expansion, no contraction in the case of 0. In such case, divergence free only. We can say that flow is divergence free. Divergence free because no expansion, no contraction only. Or we can say that that vector is solenoidal vector only. Divergence free vector or solenoidal vector when divergence is 0. If it is greater than 0, we can say the flow is away from the point or expanding, that is diverging only, expanding only. And it is less than 0 means the flow is towards the point, contracting only. So this is useful. The divergence is useful to check whether the flow is expanding or contracting at any particular position in a flow of quantity only. And gradient is useful to write the normal to any given surface. That's it. Note point. If del dot f bar equal to 0 or div f bar equal to 0, then the vector f bar is called a divergence free vector or solenoidal vector. Okay, it is about divergence. Next, its continuation, curl, last quantity. Because in this topic we are going to discuss 3 types of quantities. One is gradient, divergence, and curl. 2 are completed, and then we read the last one, curl. Curl of a vector function. Curl of a vector function. If f bar equal to f1 I bar plus f2 j bar plus f3 k bar is a vector function, then the curl of a vector function f bar is denoted by is denoted by nabla symbol. After nabla symbol, cross operation. After cross operation, F bar or small letter C, small letter U, small letter R, small letter L, curl, F bar, and defined as del cross F bar equal to curl F bar equal to, this is a cross product. An easy way to find this cross product for this three-dimensional, we consider third order determinant. Along the first row, from del and F bar, we take the common terms. From the del operator and F bar, we take the common terms. The common terms are I bar, J bar, K bar. Along the second row, from del operator or vector differential operator without I, J, K, we have the dou by dou x, dou by dou y, dou by dou z. Along the last row, from F bar vector without I, J, K, that is F1, F2, F3. And then we expand along the first round, just like determinant. Just like determinant, not exactly determinant only here. So I bar into this. I bar, delete the corresponding first row, corresponding first column, and write the determinant of these two by two, but not exactly determinant. Dou by dou y of F3 minus dou by dou z of F2. Okay, write down this. Dou F3 by dou y minus dou F2 by dou z into I bar minus J bar into, again from the first and last column, we dou by dou x of F3 minus dou by dou F1 by dou z only into J bar. Next, plus K bar into, from the first two columns, we read dou F2 by dou x minus dou F1 by dou y into K bar. I bar into F3 derivative minus F2 derivative minus, next J bar into F3 derivative, F1 derivative into J bar, plus K bar into F2 with respect to x minus F1 with respect to x. Again, the output is in terms of ijk only. In the gradient, we operated this del operator on scalar function, and this gives the vector function only. Next, we operated this del operator on vector function with the dot operation, and this divergence converts the vector function to scalar function only. Again, here we are operating the same operator on vector function with the cross operation. This resulting is the vector function only. Gradient converts scalar function to vector function. Divergence converts vector function to scalar function. Curl converts the vector function to vector function. Okay. So for this curl, input is vector function, output is also vector function only. Like divergence, we calculate the curl at a particular position in a flow of quantity only. If we calculate the del cross F bar at a particular point, then this may be either zero vector or may not be zero vector, because del cross F bar is vector only. Del cross F bar is a vector because curl converts the vector function to vector function. Output is vector. That is why this may be zero vector, may not be zero vector. So if we calculate the curl at a particular position in a flow of quantity, that may be zero vector, may not be zero vector. Based on this, we can set mathematically. So mathematically, we can set whether the flow has rotation whether the flow has rotation or not, or in a flow of quantity, rotation exists or not. That is, the flow is like this or not. Whether the flow like this expands, that is given by divergence. Whether the flow is contracting like this means given by divergence. Like that, whether the flow has rotation or not, we check it out using curl. So curl is useful to check the flow has rotation or not. And already I told that there are four types of flows. One is electric flow, next magnetic flow, next fluid flow, and next flow is air flow only. These are the four flows only. In general, we come across these flows only. Out of all these, the simplest flow is fluid flow only. Mathematically, using this curl, we can say that the rotation exists or not only. Physically, if you want to check the rotation exists or not in a flow of quantity, we consider the simple flow, that is fluid flow. Let us suppose the fluid is flowing like this. The fluid is flowing like this only. Let us suppose the fluid is flowing like this one. In this fluid flow, if we want to check the rotation exists or not, we do like this one. We take the pedal wheel. We take the pedal wheel and we place this pedal wheel in the flow of quantity only. I'm placing the pedal wheel. After placing this pedal wheel in a flow of quantity, we observe the pedal. We check that wheel rotates or not. We check this wheel rotates or not only. Suppose the wheel doesn't rotate. The wheel doesn't rotate about its fixed axis only. Doesn't rotate about its fixed axis. And this travels along with the flow. The wheel doesn't rotate and travels along with the flow. In such case, we can say that there is no rotation in flow of quantity only. Or in the fluid flow, there is no rotation only. Suppose this wheel rotates about its fixed axis and also travels along with the flow. The wheel rotates and also travels along with the flow. In such case, we can say that there is a rotation in the flow of quantity only. Physically, like this, we can check only. Mathematically, if you want to check the rotation exists or not, using curl only. So three quantities here: gradient, divergence, curl. Gradient is useful to find the normal to surface, and gradient is useful to find the normal to any given surface. Next, divergence is useful to check the flow has expansion or contraction, or to check whether the flow is expanding or contracting at a particular position in a flow of quantity on. Next, curl is useful to check the flow has rotation or not, whether the flow is rotating or not, curling or not. So these are three quantities. Right, note point number 1. If del cross F bar equal to 0 bar or curl F bar equal to 0 bar, then the vector F bar is said to be an irrotational, that is no rotation. Del cross F bar is not equal to 0 bar. Del cross F bar is not equal to 0 bar, there is no rotation. Suppose del cross F bar equal to 0 bar, irrotation, no rotation only. Not equal to 0, rotation only. Curl is 0 bar, no rotation, irrotational. Curl is not equal to 0 bar, then there is a rotation in the flow only. So curl means rotation only. Curl is 0 bar, no rotation, irrotational. So del cross F bar equal to 0 bar, curl is 0 bar, then the vector is called irrotational vector, no rotation. Irrotational vector or conservative vector. Note point number 2. Curl of gradient equal to 0 bar. Curl of grad phi is 0 bar. So gradient is a vector. Gradient is vector. For that gradient, if you find the curl, that is always 0 bar. So from this, we can say that every gradient is irrotational. Every gradient is irrotational. Next, note point number 3. Div of curl f bar equal to 0. If we find the divergence for curl of any vector function, then this is always 0. From this, we can say that, first of all, divergence is 0 means solenoidal vector or divergence free only. For any curl, if we find a divergence, that is always 0. So from this, we can say that every curl is solenoidal only. Every curl is solenoidal. Div of grad phi. In symbolic form, div means del dot. Grad phi in symbolic form is del phi. We write this as del square phi, comma, where del square equal to, or nabla square equal to, dou square by dou x square plus dou square by dou y square plus dou square by dou z square. It is a Laplacian operator in 3D only. Next, note point number 5. If div of grad phi equal to 0, in the brackets, that is del square phi equal to 0, then the equation del square phi equal to 0 is called a Laplace equation. And the function phi of x, y, z is called a harmonic function. Div of grad phi is 0. That is del square phi equal to 0. Then such an equation is Laplace equation, and phi is called harmonic function, or any solution of Laplace equation is called harmonic function. These are the note points. So from this total vector differentiation part, you have to remember like this. One is del phi. This is as gradient. Next, del dot f bar. This is divergence. Next, del cross f bar. This is curl. Next, del phi suffix p dot a bar by modulus of a bar. This is as directional derivative only. Del cross means curl. Del phi means gradient. Del cross del phi is 0 bar. Curl of del phi. This is curl of gradient is 0 bar. Or we write this as curl of grad phi or del cross del phi equal to 0 bar. Dive of curl 0. Randomly we take any scalar function, find the del phi, and for this apply the curl. Then this is always 0 bar. Randomly take the one vector function, find the curl, it is also vector. For this vector, if you find the divergence, this is always 0 only. Always. That is why every gradient is irrotational. Every gradient is irrotational. Every curl is always solenoidal only. Next, we will be 3 more results later. While doing the problems, we write the 3 more results only. Here note point number 5, next note point number 4, 5. If f bar is an rotational vector, then f bar equal to del phi, where phi is scalar potential function. Where phi is scalar potential function. Every rotational vector will be written as gradient of scalar function because from this curl of grad phi, let's observe this result. Curl of grad phi is always 0 bar. That is, every gradient is always irrotational. Gradient is vector only. If you write this in symbolic form, we write the curl as del cross and grad phi as del phi equal to 0 bar. So gradient is vector only. If you replace this with some vector f bar, then del cross f bar equals 0. Here f bar is del phi. That is the result here. This note point phi is. If f bar is rotation, then f bar is equal to del phi. F bar equal to del phi from this. Next note point number 6. This is note point number 6. Right. This is about the 3 quantities vector differentiation part. Now we'll do the problems on this. So finally, gradient is normal to surface. Next, divergence is gradient is useful to find the normal to the surface, and then divergence is useful to check the flow has expansion or contraction only, or whether the flow is expanding or contracting. Curl is useful to find the to check the rotation exists or not only. Just we are going back to this gradient. So if you find the del phi at a particular point, that del phi at a particular point is a normal to surface only. Okay. If you know the normal, we can add the unit normal vector to the surface. Or we write the note point here on. Del phi at a point capital P is a vector along the normal to the surface. The surface phi of x, y, z equal to 0 in outward direction or positive direction. So if you are finding a del phi at a point, means that is a normal to the surface. Del phi is a vector that is along the normal from this diagram. If you know the normal, we can add the unit normal vector on it. That is next node point number 2. N bar equal to del phi by modulus of del phi at a point capital P is a unit normal vector to the surface. Phi of x, y, z equal to 0. Okay. Let us do the problems on this. Problem number 1. The unit normal vector for the sphere x square plus y square plus z square equal to 9 is, we are given equation of the surface of the sphere, and the equation of the surface of sphere is x square plus y square plus z square equal to 9. For this sphere surface, we are asked to find the unit normal vector. If we find the normal vector, we can add the unit normal vector. The normal vector is given by one of the quantity gradient. Let phi equal to x square plus y square plus z square minus 9 scalar function equal to 0 is an equation of the surface. Then del phi equal to grad phi equal to del phi equal to gradient phi equal to dou phi by dou x into I bar plus dou phi by dou z into j bar plus dou z by, that is, this is y, dou phi by dou z into k bar. Now this is a formula to write the gradient of a scalar function. Phi with respect to x into I bar, phi with respect to y into j bar. Next, phi with respect to z, dou phi by dou y into j bar plus dou phi by dou z into k bar, which implies del phi equal to, for this scalar function of 3 variables x, y, z, we require the partial derivative of phi with respect to x, that is 2x into I bar plus 2y into j bar plus with respect to z 2z into k bar. This del phi is a normal to given surface, is a normal vector. It is a normal vector. If you know the normal, we can add the unit normal on. Therefore, n bar equal to del phi by modulus of del phi equal to 2x into I bar plus 2y into j bar plus 2z into k bar divided by under root of 2x square plus 2y whole square plus 2z square equal to. From the numerator 2 is common, from the denominator 2 square is common. If it comes out, that becomes 2 to get cancelled. After taking a 2 square outside from the root, under root you will have x square plus y square plus z square. But x square plus y square plus z square is 9. So x I bar plus y j bar plus z k bar divided by root 9. This is equal to x I bar plus y j bar plus z k bar divided by 3 is a unit normal vector to the given surface. Again, we require all this in the next subtopic, vector integration. Next, problem number 2. The directional derivative of the function phi of x, y, z equal to x square y z plus 4x z square. X square y z plus 4x z square at the point 1 minus 2 minus 1 along 2 I bar minus j bar minus 2 k bar is we require the directional derivative of the function phi in the direction of 2 I bar minus j bar minus 2 k bar at the point 1 minus 2 minus 1. Let us consider the given data first. Let phi equal to the given scalar function x square y z plus 4x z square, comma, take the given direction vector as a bar equal to 2 I bar minus j bar minus 2 k bar, and given point as capital P equal to xyz is here 1 minus 2 minus 1. To find the directional derivative also, we require the gradient. So let us find the gradient first. Del phi equal to dou phi by dou x into I bar plus dou phi by dou y into j bar plus dou phi by dou z into k bar. This is equal to phi with respect to x is 2xyz plus 4z square into I bar plus with respect to y is x square z plus 0 into j bar plus with respect to z is x square y plus 8xz into k bar. But we require this at a particular point, del phi at P. That is substitute x equal to 1, y equal to minus 2, z equal to minus 1. The quotient of I is dou phi by dou x. Differentiate phi partially with respect to x, 2xyz plus 4z square. Next, the quotient of j bar is dou phi by dou y. Differentiate phi partially with respect to y, x square z on. Next, the quotient of k bar is dou phi by dou z. The partial derivative of phi with respect to z, x square y plus 8xz on. Now substitute x equal to 1, y equal to minus 2, z equal to minus 1 and write the value. Eight I bar minus j bar minus 10 k bar. Now we know the del phi at a point. Now we consider the directional derivative. dd equal to del phi at p dot a bar by modulus of a bar. Right, and simplify this. Eight I bar minus j bar minus 10 k bar dot a bar is 2I bar minus j bar minus 2k bar divided by under root 2 square plus minus 1 square plus minus 2 square. Therefore, dd equal to, after simplification, now after simplification we get this value. This is the derivative of the function at this point in the direction of the given vector only. Next, problem number 3. In what direction starting from, sorry, in what direction starting at 0 comma pi by 2 comma is phi of x comma y equal to e power xy into sine of x plus y changing the fastest. In what direction starting at this point is phi changing the fastest? That is, we require the fastest change. In what direction? That is, we are asked to find the direction vector along which the fastest change of phi occurs. We require the direction vector along which fastest change occurs on. Already we know that the maximum rate of change or greatest rate of change or fastest change occurs in the direction of normal when theta equal to 0. When theta equal to 0, the direction vector a bar coincides with normal only. That is why the maximum occurs in the direction of normal only. In what direction maximum changes or the fastest change occurs means normal direction only. Again, normal is grade phi. So we have to find the gradient of scalar function. Given phi equal to e power xy into sine of x plus y, and the point capital P equal to 0 comma pi by 2 only. We know that the maximum rate of change occurs in the direction of normal, del phi. So in what direction fastest change occurs means in normal direction. First of all, that happens when theta equal to 0 only. For theta equal to 0, direction vector coincides with the normal. That is why normal is the direction vector only. Now del phi equal to phi with respect to x into I bar. Differentiate differentiate this phi partially with respect to x. Product of two function, UV rule. First, exponential derivative exponential, xy derivative y e power xy into sine of x plus y plus, again sine derivative cos, inner function derivative is 1, e power xy into cos of x plus y into I bar plus, next dou phi by dou y. Again both are having variable y, so use the product rule, x into e power xy into sine of x plus y plus e power xy, derivative of cos, sine is cos, x plus y derivative with respect to y is 1 into j bar. This is the del phi gradient. But we require this at a particular point, which implies del phi at P, x equal to 0, y equal to pi by 2. X equal to 0, x equal to 0, e power 0, 1. Here x equal to 0, y equal to pi by 2, sine pi by 2, 1 into y pi by 2 plus x equal to 0, pi by 2, cos pi by 2, 0 into I bar plus 0 plus cos pi by 2, 0 into j bar. Therefore, del phi at P equal to pi by 2 into I bar plus 0 into j bar is a direction vector along which maximum rate of change occurs or fastest change occurs. Problem number 4. The vector v bar equal to e power x into I bar plus 2y into j bar minus k bar is option A, divergence free but not irrotational. Option B, irrotational but not divergence free. Option C, both irrotational and divergence free. Option D, neither irrotational nor divergence free. Del dot f bar is a divergential. If this is equal to 0, then divergence free vector only. To check the function is irrotation or not, we have to find it del cross f bar. Del cross f bar equal to 0 bar, then the function is irrotational, that is no rotation. So to check the given vector function is irrotational or not, divergence free or not, we have to calculate divergence and curl on. Now, what are the vector notation is given like this v bar? We consider our usual notation for vector as f bar on. Let f bar equal to f1 I bar plus f2 j bar plus f3 k bar, because we have written all those with the notation f bar only. So we are taking this given vector as like this: e power x into I bar plus 2y into j bar plus minus 1 into k bar. It is a given vector. Now to find the divergence, we consider the formula. Then del dot f bar equal to div f bar equal to dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. It is a formula to write the divergence of any given vector function, which implies del dot f bar equal to, the first term is f1 with respect to x. This is the f1 with respect to x is e power x plus, next this is f2 with respect to y is with respect to y is 2 plus, this is f3. This is f3 with respect to z is 0, which implies del dot f bar equal to e power x plus 2. This is not equal to 0. This is not equal to 0. Whenever divergence is not equal to 0, we can say that f bar is divergence free vector or solenoidal vector. So divergence is equal to 0, divergence free only. But here divergence is not equal to 0 means not a divergence free only. Therefore, f bar is not a divergence free. Del dot f bar equal to 0, the vector is divergence free vector. Not equal to 0, not divergence free only. So both irrotational divergence free is wrong. Divergence free is also wrong because not a divergence. So either B or D must be correct. Then we have to calculate the curl. Now del cross f bar equal to curl f bar equal to third order determinant I bar, j bar, k bar, dou by dou x, dou by dou y, dou by dou z. F1. F1 is e power x, F2 is 2y, and F3 is minus 1. We expand, which implies del cross f bar equal to I bar into derivative of this function with respect to y minus derivative of this function with respect to z, that is 0 minus 0. into I bar minus j bar into derivative of this function with respect to x 0, derivative of this function with respect to z, that is also 0, into j bar plus k bar into derivative of this 2y with respect to x minus derivative of e power x with respect to y, 0 minus 0 into k bar, which implies del cross f bar equal to 0 into I bar plus 0 into j bar plus 0 into k bar. Therefore, I'll write this del cross f bar equal to 0 vector. 0 bar means 0 vector. Only 0 means not a 0 vector. 0 value 1. So it is a vector with a 0 magnitude. That is why this is a 0 vector. We are writing this as 0 bar. Curly 0 bar means irrotational, no rotation. Therefore, f bar is an irrotational only. Irrotational vector, that is no rotation. Hence, the given vector function is irrotational but not divergence free only. But not divergence free. So answer is irrotational but not divergence free. B only. Hence, option B is correct. Next, problem number 5. The values of A, B, and C, so that the vector V bar equal to x plus 6y plus az into I bar plus 2bx minus 3y plus 2z into j bar plus 4x plus 2cy plus z into k bar is an irrotation. That is, we are given one vector function along with the unknown a, b, c, and we are asked to find the 3 unknown values a, b, c only. To find the 3 unknown values, we require minimum 3 equations. To get the 3 equations, we require the condition. That condition is already given. What is the condition here? Irrotation. Use the rotation condition and try to write the values of a, b, c only. Irrotational condition means curl is 0 bar only. Use the curl equal to 0 bar and solve for a, b, c only. Let f bar equal to f1 I bar plus f2 j bar plus f3 k bar. I'm taking the v bar x plus 6y plus az into I bar plus 2bx minus 3y plus 2z into j bar plus 4x plus 2cy plus z into k bar. Already given that irrotation only. So consider del cross f bar equal to 0 bar for irrotational. Which implies I bar, j bar, k bar. Dou by dou x, dou by dou y, dou by dou z. X plus 6y plus az. 2bx minus 3y plus 2z. 4x plus 2cy plus z, which implies derivative of this function with respect to y, that is 2c, with respect to z minus 2 into I bar minus with respect to x 4 with respect to z a into j bar plus with respect to x 2b with respect to y 6 into k bar equal to 0 bar. But 0 bar is a vector with a 0 magnitude. We write this as 0 into I bar plus 0 into j bar plus 0 into k bar. If we compare both sides I bar, j bar, k bar coefficients, 2c minus 2 equal to 0, 4 minus a equal to 0, and 2b minus 6 equal to 0. Therefore, c equal to 1, a equal to 4, and b equal to 3 odd. So for these values of a, b, c, the given vector function becomes irrotational, otherwise not irrotational. Next, problem number 6. If r bar equal to xi bar plus yj bar plus zk bar and r equal to modulus of r bar, then gradient of sine r equal to, given that r bar equal to xi bar plus yj bar plus zk bar, position vector of any point in space, which implies its length or magnitude, r equal to modulus of r bar equal to under root of x square plus y square plus, it is also same as r square equal to x square plus y square plus z square on it, which implies dou r by dou x equal to, it is a function of three variables. If we differentiate this function partially with respect to x by using root x formula, 1 by 2 root of x square plus y square plus z square, inner function derivative with respect to x 2x equal to 2 get cancelled, x by, again this is same as r. So dou r by dou x is x by r. Similarly, we write the dou r by dou y, that is y by r, and dou r by dou z equal to z by r. The gradient formula is like this: del phi grad phi equal to dou phi by dou x into I bar plus dou phi by dou y into j bar plus dou phi by dou z into k bar. Here phi function is sine r. In place of sine, in place of phi, write the sine, and then differentiate. We get the function. We get the gradient of that function. Without finding the derivatives directly, we can add the gradient of sine r because it is a function of r only. I'll give the shortcut formula for this only. Since del of any function of r equal to r bar by r into f dash of r. It is a direct shortcut formula for any function of r. Using this directly we can write it without finding all these, without finding all this. Using the, by general method gradient formula, if you want to find, we can find, or by using this shortcut formula within one step we can write down. Therefore, del of sine r, compare this del of sine r with del of f of r. That is, in place of f of r we have this function. So replace f of r with a sign r on right hand side. That is r bar by r into f dash. F dash means here, this is ordinary derivative, d by dr of f of r function only. Derivative of f of r with respect to r. Sin derivative with respect to r is cos r. That's all. This is the form. If we know this formula, we can add the within one step only. Here, the formula is this. This is the formula here. We should write this. Del of any function of r equal to r bar by r into f of r. Right. Next, problem number 7. If r bar equal to xi bar plus yj bar plus zk bar and r equal to modulus of r bar, then div of e power r into r bar equal to. It is similar to previous problem. In the previous problem, it was asked to write the gradient, but here it is divergence. Like previous problem, we use the direct formula for function of r. Now first write the formula. The formula is del dot any function of r into r bar equal to 3 into f of r plus r into f dash of r, comma, where f dash of r d by dr of f of r. Divergence of any function of r into r bar on. Therefore, for given problem, del dot e power r into r bar equal to. If we compare this given with the general formula, in place of f of r, we have e power r. So on right hand side, replace f of r with e power r. 3 into, wherever f of r is there, in place of that, write the e power r. 3 into e power r plus r into e power r first derivative with respect to r, that is e power r. 3 plus r into e power r. It is the result. Next, problem number 8. If r bar equal to xi bar plus yj bar plus zk bar and r equal to modulus of r bar, then curl of r power 4 into r bar equal to. This 8th problem is similar to previous 2 problems only. 6th one is gradient, 7th one is divergence, 8th one is curl. It is only difference. This is very simple formula. Symbolic formulate. Del cross any function of r into r bar is equal to very simple result, that is 0 bar. That's it. For any function curl is 0 bar, then such a function is called irrotation. So here f of r into r bar is irrotation. Therefore, for given problem, del cross r power 4 into r bar equal to. If we compare the required result with the general result, f of r will be r power 4. But whatever the function here, always its result is 0 bar. It is the answer. We write these 3 results in page number 100. Del dot f of r into r bar equal to 3f, here f dash, 3f of r plus r into f dash of r. del cross f of r into r bar equal to 0 bar. That's from the vector differentiation part. You have to remember all this. You will be given problems on these. So with this 108 page, the problems on vector differentiation are completed. With this, vector differentiation part is completed. Next, we start the last subtopic, vector integration. This vector differentiation, we have discussed about three quantities, gradient, divergence, curl. Along with these three quantities, one more thing is directional derivative. Okay, let us start last subtopic, vector integration. In the vector integration, we'll discuss about three types of integrals. One is line integral in short form, L dot I. Next, surface integral in short form, S dot I. And volume integral in short form, V dot I. Among these three integrals, the three transformations which are given by the three theorems, Green's theorem, Gauss divergence theorem, and Stokes theorem. Among these three integrals, the transformations are given by three theorems. One is Green's theorem, short form G dot T, Gauss divergence theorem, G dt, and Stokes theorem, short form S dot T on. Green's theorem is a relation between line integral and double integral only. Gauss divergence theorem gives the relation between surface integral and volume integral. Stokes theorem gives the relation between line integral and surface integral. So these three theorems are required in easy way to evaluate line surface integrals. These three theorems are required in easy way to evaluate line and surface. Okay. Let us discuss about line integral first. In short form, L dot I. Now, before going to this line integral, first we'll discuss about something. For u equal to f of x, y, z, the derivatives are partial derivatives with respect to x ux, with respect to y uy, with respect to z uz. This ux is rate of change of u along the x direction. Uy is rate of change of u along the direction, along the y direction. Uz gives the rate of change of u along the z direction. These three derivatives are rates of change of u along the coordinate axis direction. Suppose if you want to find the rate of change of u other than coordinate axis direction, that is arbitrary direction in space. If you want to find the derivative of this function along some arbitrary direction in space, such a derivative is called directional derivative. This is from previous topic. These three derivatives are along the coordinate axis only. dd is the directional derivative along the arbitrary direction in space only. These are the coordinate axis direction. This is the space direction, arbitrary direction in space. Similar to this, integral x equal to a to b f of x dx. Integral y equal to c to d f of y dy. Integral z equal to a1 to a2 f of z dz. Or integral t equal to a to b f of t dt. Like these three derivatives ux, uy, uz, these are the single integrals. Z-axis, y-axis, x-axis. Now first integral, integral x equal to a to b f of x dx. It is a single integral. We evaluate this integral along the x-axis because along the x-axis, we can obtain the projection of this curve f of x from a to b only. Along the x-axis, we evaluate this integral from a to b only because along this x-axis, this part is the projection of the curve in space y equal to f of x. That's why we evaluate this integral along the x-axis from a to b only. Similarly, integral c to d f of y dy. Function is in terms of y. So for this curve y, for this curve f of y, the projection will be on y-axis only from c to d only. So we evaluate this second integral along the y-axis from c to d only. Next, function is in terms of z with respect to z. We evaluate this integral along the y-axis, along the z-axis from a1 to a2 only. It is the integral along the z-axis. The first integral is along the x-axis from a to b. Second integral is along the y-axis from c to d. Third integral is along the z-axis from a1 to a2. Similarly, last integral is integral along the t-axis from a to b like this. All these single integrals are the integrals along the coordinate axis only. Just like ux, uy, uz, derivatives along the coordinate axis. These are the integrals along the coordinate axis. Suppose if you want to find the integral, along some arbitrary curve in space from a point A to point B, just like this here. If you want to find the derivative along some arbitrary direction, if you want to find the derivative of the function along some arbitrary direction, such a arbitrary direction derivative is directional derivative. In the same way here, if you want to find the integral of the function along some arbitrary curve in space, such an integral is line integral only. These are the integrals along the coordinate axis only. If you want to find the integral along the curve in space, arbitrary path, in space along arbitrary path, such an integral is called line integral only. So if you apply some force on any body, that force, if you apply the force on any body, that body displaces from one position to other position. After displacing, if you observe the path, that path may be like this, the path may be like this, or path may be like this, or path may be like this, path may be like this, from one position to other position. So the total work done by the particle, the total work done by the force vector is the line integral. So line integral is useful to find the work done by the force. This line integral is same as the work done only. Just observe this. These are the integrals along the coordinate axis only. And if you want to find the integral along some arbitrary curve in space, then such an integral is line integral. Line integral is here work done by the force vector. Right. This is about line integral. These are the integrals along the coordinate axis. Integral along the curve in space is the line integral. These are the derivatives along the coordinate axis only. Derivative in arbitrary direction is directional derivative only. Similar to directional derivative, it is a line integral. We extend this to two variable only. Double integral over R1 f of x comma y dx dy. Double integral over R2 f of x z dx dz. Double integral over R3 f of y z dy dz. Like these three integrals, these are the integrals only. These are the double integrals. These are the single integrals only. Now this is the integral. The first integral is the integral over the xy plane. Because R1 region is the projection of this curve f of x comma, projection of the surface f of x comma y only. So we evaluate this first integral over the xy plane, and we evaluate the second integral over the xz plane or 2 only. We evaluate this integral over the yz plane. So these three integrals are the integrals over the coordinate planes xy, xz, yz only. Like these integrals along the coordinate axis only. But always we may not require the integral over the coordinate plane. Sometimes it is required to find the integral over the space, over the surface in space only. over the surface in space only. If you want to find integral over some region, that region is in space. These are the integrals over the coordinate planes only. Suppose if you want to find an integral over the region in space only, arbitrary region in space, such an integral is double. So here such integral is here surface integral. Here the integral along some arbitrary curve in space is line integral. Here the integral over the arbitrary surface is the surface integral. Coordinate planes regions means double integral only. If you want to find integral over the arbitrary region in the space, then such a integral is the surface integral only. So the surface integral is same as the flux across the surface, the rate of flow across the surface. So line integral is the work done, and the surface integral is flux across the surface. This is flux, this is the work done. That's in easy way to find this line and surface, we require these three transformations. For this, we require the volume integral. So line and surface integrals are work done and same as the flux here. Line is the work done, surface is the flux. Okay, let us write the line integral. If a vector Okay, now it is working. Write this. If a vector function f bar is defined when at every point on the curve C. Again, it is problem. On the curve C, then serious difference. Okay, there is a technical problem here for writing the pen. So we stop the today's class and we continue this tomorrow. We close the today's class session. Tomorrow we continue this topic on. So tomorrow is the last class for this vector calculus and for total calculus part. Okay, we'll see tomorrow.
Sir, no doubt session. Hello. Sir.
Okay, let us have a doubt session. Like screw open and close. Reflector. Hello.
Hello.
Hello. Ask me. Hello.
98F, sir. Page number 98F.
98.
I just missed the screenshot.
Okay.
Yes, sir.
98. This one. Are you asking about this one? Hello.
Yes, sir. Yes, sir.
Okay.
98 page number.
Which page?
Yes, sir. Yes, sir. Got it, sir.
Got it?
Sir,
Oh.
100.
Your voice is not audible.
Means different formulas for that. Different.
Hello. Hello. Hello.
Hello. Hello.
Hello. Now it is audible. You can ask.
Hello.
Hello.
Yes, actually.
Again, it is gone.
You wrote different formulas for.
Hello.
Hello. Sir, now am I audible?
Not audible.
Hello. Now?
Hello. You can ask.
Hello.
Hello. It is audible.
Sir, in the page number 100.
Page number 100.
Sir,
Okay.
in that page number 100, you wrote different formulas for that
Yeah,
vector differentiation, na, sir?
That is
Sir,
overview
here
of
in
this
that
vector
last three
differential.
formulas, is there any reason for that?
You have to remember these last three formulae. If you want to
Sir,
remember,
for that
remember.
last three formulas.
Hello.
Sir, is there any explanation for these three formulas?
No formula. Directly for any function of r, I wrote here. Here f of r may be sine or cos or log or e power r, 1 by r power n, anything, shortcut formula directly. Otherwise, we can use this formula. Instead of this formula, we can use this gradient.
Okay.
Instead of this del dot divergence, we can use this del dot f bar formula.
Okay.
That is the only difference. Okay.
Sir, and what is the difference between that f of function of r and r vector?
Function of r and r vector. F of r means function.
Yes, sir. Here, sir, f of r and r vector is
magnitude. F of r is a scalar function. R bar is a vector. Hello.
Okay. Okay, sir.
That r is a magnitude of this r bar.
Okay, sir. And harmonic function here means what, sir?
Solution of this Laplace equation.
And sir, here in the above note point.
Note point number 6.
Sir, harmonic means what physics mean? It means, sir.
You will find this physical meaning.
Here only, this page only.
Physical meaning in EMTL subject. Hello. Purely
so mathematically, does it mean something? Means harmonic function?
Solution of Laplace equation. Mathematically, solution of Laplace equation.
Oh.
The Laplace equation satisfies with any function, then such a function is called harmonic function. Purely physical meaning means you find that in EMTL.
Can you give any example? Sir, here can you give any example means by a
phi equal to x square minus y square plus
Hello?
z square. 5x 2x 5xx 2 5y minus 2y 5yy minus 2. Next 5z0 5zz 0 only. Sum of all this is 0. So del square phi is 0 here. This function is called harmonic function.
Okay.
This del square phi will satisfy with this function only. It is a solution of this equation. It is a Laplace equation and this function is harmonic function.
Okay, sir. Okay. Got it. Thank you.
Audible, sir.
Audible. You can ask.
Sir, yesterday you gave one question, sin x by x, that you didn't solve in limits.
That is a previous gate question, last year gate question. That is similar to our problem e power y square problem.
Okay, I just want to know is answer 2 correct for that?
You want answer for that question?
I got answer as 2. I just want to know whether it is correct or not.
Okay, I will check it on.
Okay.
Yeah, 2 is correct.
Sir, page number 103.
Is it?
Sir, right. Sir, here why didn't we divide by pi by 2, means by its magnitude, since we are dealing with direction, sir?
Actually, we are asked to find only direction vector, along which maximum change occurs only, fastest change.
Sir, it is n cap is what? Vector by its magnitude, na?
Yeah, that is unit normal vector. But here we are asked to find the direction vector. This is del phi, and this is some direction vector. If this makes an angle theta, when theta equals 0, this direction vector will coincide with the normal vector only. So for theta equals 0, maximum rate of change occurs for directional derivative. So we are asked to find the direction vector a bar. That is same as here del phi only.
Okay, sir. Got it, sir. Sir, page number 107.
07. Okay.
Sir, here is there any formula for means del square sine r for means second Laplacian equation? Is there any formula del square?
Del square. Suppose if we want to find the del square of f of r, we read this as del dot del f of r. Okay. Del dot del of f of r is already known. R bar by r into f dash of r. Okay. Here again, this is some. We can use the next formula. Del dot some function of r into r bar. Again, 3 into f of r. That is f dash of r by r plus and r into f dash of r. That is here f dash of r by r derivative. If we simplify this, we get the result.
Okay. Sir, for Laplace equation is what? Del square f is equals to 0.
Yeah.
Okay. And del square x is equals to what? Gradient of divergence of x minus curl of x. Means both are equal.
No,
Does it?
Both are different. Del square phi means here del dot del phi. That's a divergence of gradient. This is the divergence of gradient only.
The expansion of del square phi means in EMT we wrote as gradient of divergence of x minus curl of x. Means if we equate to this Laplace equation to 0,
repeat it.
Gradient of divergence of x.
Gradient of divergence of x equal
minus
to
curl of x. Curl of x.
Curl of x. I think this is the formula. Del cross f bar equal to
Yeah. Right.
del of del dot f bar minus del square f.
Yeah. If we equate del square f is equals to 0,
Right, we'll get same
then
thing on.
means what is the physical significance of this, sir? Because one is a rotational quantity and another is divergence, no, sir?
For this, we cannot say directly. For everything, we cannot say physical significance only. This is some identity only.
Okay.
This is some identity.
Okay, sir. Thank you, sir. Got it, sir.
Right.
Thank you.
Hello.
Done, sir. Done.
Okay. Hello. Hello.
Hello.
Hello. Tell me.
Yes, sir. Good evening, sir.
Good evening.
So page number 108F.
108F. Yeah.
Sir, I didn't understand this 8 sum, sir. How did it become 0?
This one.
Yes, sir.
Here I wrote the formula, direct formula here. Del cross f of r into r bar equal to 0 bar. And we are asked to find del cross r power 4 into r bar. If we compare the required result with the general formula, r bar, both are same. In place of f of r, whatever the function is here, r power 4, sine or cos or log or r power n, anything, curl is always 0 on bar.
Okay, sir. In the
If
7th
you want to
formula. Yes,
do this problem by using curl, then do like this only. I bar, j bar, k bar, dou by dou x, dou by dou y, dou by dou z. And this r bar is xi bar, yj bar plus zk bar only. So in that case, the f1 function will be x into r power 4. Here y into r power 4, z into r power 4. Then expand, simplify. We get this 0 bar finally.
yes, sir. Thank you,
If you
sir.
want to do like that, we can do. Otherwise, we can remember this formula directly.
Yes, sir.
Okay. Hello. Hello. Hello.
So that's it, sir. Thank you. Sir.
Okay. Hello.
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 Hello. Audible, sir?
Audible. You can ask.
Sir, what is the value of curl of A cross B vector?
Curl of A cross
A
B
cross
vector.
B. Yes,
That
sir.
is
How
del
to
cross
proceed that, sir?
del
A
cross
cross
A
B.
bar.
Yes, sir.
Del dot B bar into A bar minus.
Sir, it's not visible.
Not visible.
No, sir.
Use the curl formula. That is determinant. I bar, J bar, K bar.
Okay.
Hello.
Yes, sir. Yes, sir.
What are the A bar, B bar here?
Sir, it is an vector. Normally, we take x I cap plus yj cap.
If we have a particular vector A bar, B bar, first we find the cross product of A bar, B bar. That cross product will be one vector. For that vector, we find the curl again by using same determinant.
Okay, sir. Okay. Sir, it is not an identity so that...
No. Not an identity. Because A bar, B bar are some vectors only. We should know that vectors only. If you know the vectors, first we find the cross product of two vectors A bar and B bar. That will give some vector. For that vector, we find the cross product. That is curl.
Okay, sir. That's all, sir.
Oh, okay.
Good evening, sir.
Good evening.
Sir, you said for curl vector, it helps to find the rotation like that. For gradient and divergence also, you said something, right, sir? I missed it.
Gradient is useful to write the normal vector to any given surface.
Okay, sir.
And divergence is useful to check the flow is expanding or contracting only. That is, flow is away from the point or flow is towards the point only.
Is divergence.
Yeah.
And page number 105F.
105. Okay.
10. In that, sir, you said zero vector. So how the J become plus, sir? So is it plus?
No. Actually, this minus 0 means 0 into minus also 0 plus 0. We can write anything.
So it's nothing for a zero vector is not
0
problem.
No. It doesn't matter.
Okay,
Not a
sir.
problem.
Okay, sir. Thank you.
Okay. Hello.
So that's also thank you.
Oh, okay. Okay, I'm closing this doubt session also.